Valence bond theory. All right, so let's see if this is going to work or not. Let's look at sigma and pi bonds. If we look at p orbitals, let's say I have a p orbital like this. There are two ways so that p orbitals can overlap. Okay? And so if I take two p orbitals, the two ways that they can overlap would be in a sigma bond. In a sigma bond, what's going to happen is just one of the lobes on the p orbital will overlap. And so here, this would be an example of atom A and atom B. We have two p orbitals. We'll just put them on their side and overlap it here. If I draw a line across the internuclear axis here, then I see that overlap occurs within the internuclear axis, and the overlap region is going to have a higher concentration of dots. That is a higher concentration of electron density. What happened to the projector? Shoot. And so this would be an example of a sigma bond. This is not a sigma bond. You know, one of the common errors is that people will overlap it like this. And so here we have atom A, here we have atom B. If we're looking at atom A and atom B, this would be just this direct bond here, a sigma bond. Here, we would have a kink in the bond. You normally write a kink line for the bond. No. That would be it. So this is wrong. It has to be direct, straight on overlap. Now, there's one more way that the p orbitals can bond, and that's by a pi bond. Sigma bond. A pi bond is like this, where we overlap the four lobes here. And so you can see this overlap here, and there's going to be overlap here. But if we look along the internuclear axis, we'll just dot as a green line here. There's no overlap here. In fact, there's a node along the internuclear axis that is no electron density to be found there. And so the electron density is concentrated in different parts of the molecule. And so here the electron density is concentrated here. There's going to be some electron density here and some electron density here, but you can see in the overlap region it's going to be greater electron density. And therefore, the nuclei are going to be drawn to this electron density like this. Okay. In a pi bond, the nuclei are going to be drawn not straight to each other, but in this region. In this region, we're going to have electron density above and below the internuclear axis. And so with this electron density above and below, then the nuclei are going to be attracted to this region above here, and this region below here, above and below. And so if it's being attracted to the regions above and below, then we're going to have a net forward. You just draw a triangle. The net forward is going to look like this. And so if we sum up these two vectors, these two arrows, we get a attraction like that. And so again, pi bond is going to attract. Now, which would you assume is stronger? You know, all things being equal, which would you assume is stronger, a pi bond or a sigma bond? A pi bond? A pi bond because it's still two electrons. You have to think, you know, 2 electrons total in this share. Here we have 2 electrons total. And so perhaps I didn't draw the density right. You know, the density here will be much more concentrated in the axis. And so we have the same number of dots here. And you might think the pi bond's more stronger because it's got 2 overlaps. So you think 2 overlaps are better, but it's not the overlaps that's holding the nuclei together. It's the attraction of the protons in the nucleus to the negative charge. So there's negative charge here, negative charge here. And so when we look at the attraction, I didn't draw the arrows proportionately, but when we look at the attractions, it turns out that the sigma bond is stronger. The sigma bond is stronger because it has electron directly between the nuclei, whereas in a pi bond, it's less. And so this is stronger. These are weaker. But it's relative. Okay. Unfortunately, I have technical difficulty here. This is not working. Let me reboot this computer. Shoot. I was hoping to just do PowerPoint, especially for chapter 16. So I want to whiz through that, but I guess I'll have to draw everything out on the board now. Okay. And do you see why it's stronger? It's stronger because the nuclei are going to be attracted directly to each other rather than above and below here. And for pi bonds, we don't draw them like this either. You know, a common mistake is people will draw it in all kinds of weird angles. Does that look very good? No. Bad. There. Okay. When do we see pi bonds? The only time we see pi bonds is when we have multiple bonding occur, that is double bond and triple bonds. That's when you'll see pi bonds. So far, we haven't seen any pi bonds. Let's switch this thing on. So, let's take a look at an example of pi bonding here. For example, I'll just do one of the molecules in your list. Actually, maybe it wasn't on your list. Let's take a look at bicarbonate. An example here. Bicarbonate, when you draw the Lewis structure for bicarbonate, you don't necessarily have to be accurate in terms of 3D representation. So we come up with a structure that looks like this for bicarbonate. And it turns out there are going to be two resonance forms for this. And two resonance forms are going to be what we had drawn up earlier. Actually, I did this yesterday, right? And then we have the resonance hybrid. The hybrid. When we do valence bond analysis, VV analysis will pick one of the resonance forms. To do VV analysis on the hybrid is a bit more complicated. And so we aren't going to do valence bond analysis on hybrids. We're just going to do valence bond analysis on a specific, and it doesn't matter which resonance form you pick because both of these resonance forms are equal in terms of energy. Choose one. Hybrid VV analysis, difficult. Because there's some kind of in between, you know, like some kind of percentage, S and P. And so, you know, when we look at the hybridization here, what is the hybridization on this one? SP3 in this one? SP2. In the hybrid, what is it? The SP3 or SP2? Sometimes it's easier to determine. So we pick one of these. And so let's pick this one. Now, you know, this isn't really a three-dimensional structure because it shows everything flat in the plane. And so what we're going to do is we'll look at each atom one by one. Hydrogen's hydrogen is just the S. This oxygen, let's look at that oxygen first. Maybe we'll start with the carbon. Let's start with the carbon. The carbon is the carbon's sp2. So what's the energy level diagram look like for sp2? How many orbitals? 3. You can always figure out how many orbitals by counting. Just one s, 2 p's gives me 3 orbitals, so I have to have 3 sp2 orbitals. sp3, you know, 1s, 3 p's, that's going to give me 4 orbitals. So next step is to figure out how many electrons. How many electrons does carbon have here? How many electrons? 4. That's right. So put them in 1, 2, 3, 4. So look how I filled this diagram. When you look at how I filled this diagram, it tells me that carbon has 1 lone pair and 2 bonds. Is that what carbon shows in this structure? No, this is wrong. It can't be. This can't be. It can't be because there's no lone pairs on carbon. So is it really sp2 hybridized? Yeah, it is, but I'm missing something. Let's redo it. When I have sp2, that's only 3 orbitals. That's 6 electrons. That isn't even an octet. How am I going to get 8 electrons in an octet in there? Because there's a p orbital here. And this p orbital is unhybridized. Now when I fill this, I got 1, 2, 3, and then I put the 4th one in the p. It's got to be that way. And so let's take a look at this. So when we have sp2, there are 2 ways of drawing it, right? Let's see which structure I'm going to draw. Let's see. Like that. I'm going to draw this one here. We'll choose one. We can choose that one. And so here I'll have a carbon. But you know, when I draw my sp2, I kind of draw it the same way. You know, sp2 typically I draw like this in the side view. So this will be sp2, sp2, sp2. So I got my 3 sp2 orbitals in there. Now, I'll call this, I'm going to call this oxygen 1. And I'll call this oxygen 2 here. And then we'll call this oxygen 3 here. There are 3 different oxygens here. And so what I'm going to do is I'm going to bond oxygen 1 over here. Yes, but before I do that, let's fill these orbitals with electrons. And so I'm missing 1 orbital. Where does that orbital go? This is why I want you to label every lobe, or every orbital, sometimes not every lobe, because I'm missing 1 orbital. Where is it? It's the p orbital on the z. And here, I'm going to label this like this. Should I label it like this? You know, I don't label it like that because if I label it like that, it makes it look as if there are 2 p orbitals rather than 1 p orbital. And so I need to get rid of one of these p's. Let's get rid of that. Because there's only 1 orbital there. And that p, there's 1 electron in that p. Right here. That's it. All right, now let's take a look at the double bond. The oxygen Oxygen 1 is what? Hybridization. It's oxygen 1. sp2. And so this oxygen 1 is sp2 as well. And so let's go over here and write down. This is carbon. Then we have oxygen 1. Oxygen 1 is sp2. And then there's an unhybridized P. This is oxygen 1. How many electrons does oxygen 1 have? 6. How do I fill these? Well, I go 1, 2, 3, 4, 5, 6. Does that look right? It can't be, even though, normally we fill the lowest energy orbitals first and then fill the higher energies, but this can't be. What has to happen is this. What has to happen is we got to promote one of these electrons. Why? So we can get more bonds. Get more bonds in an octet. You'd be better off energetically. Okay, but if I bond the oxygen with the carbon, they're going to share these electrons. If they share the electrons, we're going to put carbon spin up. That means I have to put oxygen spin down in order to share. And so this is how the double bond is going to work. What's going to happen here is this. Oxygen has an sp2. Oxygen's sp2 bigger or smaller than carbon's? What do you think?
Bigger.
Well, what happens is you go from left to right across. Do things get bigger going this way or smaller? Yeah, oxygen sp2 is going to be smaller. Maybe we'll show that here. Okay, and so it looks like an oxygen sp2, we form an sp2 sigma bond. And so that means oxygen is going to come in here. This is oxygen 1. And the sp2 orbital here is going to form a sigma bond like this. That means carbon, there's only one carbon. The carbon sp2 is going to come in here and share an electron like this. We'll just show the electron a little differently. And so what we end up with is an sp2 sigma bond. sp2 sigma. And so we got electron density directly in the internuclear region. And then oxygen has 2 lone pairs in the other sp2 orbitals. And so there's going to be one sp2 orbital coming out, this, and then one sp2 orbital going in. And both of these will have a lone pair here. We got 2 lone pairs like that. And then if we look at oxygen, oxygen has this unhybridized P right here, like carbon. So there's a p orbital here. And so we'll have an electron like this. Now, even though the p orbitals look far away, they're going to overlap. And so we draw a line connecting them since there's some distance there, but really they're, it doesn't end here. The distribution goes out. I could put the electrons in the upper lobes or in the lower lobes or somewhere between. But do you know what we form here? We form a p-pi bond. And so what a double bond consists of is a pi bond and a sigma bond. And so if we were to look at the carbon-oxygen bond, we're going to have a total of 4 electrons in the bond. And these are 4 electrons here, 2 in the sigma, 2 in the pi. And then as far as electron cloud distribution goes, a double bond looks like this. Double bond will have some sigma bonding interaction here from this. So there's going to be electron density here, in the internuclear region, axis, and up here, above the axis, internuclear axis, and below. And so this would be a pi bond here. A sigma bond would just be missing this part above and below. And even though some people miscount this, they count 1, 2, 3 bonds. Is this 3 bonds? No, it's actually just 1 and then 2. That's just 2 bonds. Now, with a pi bond, we lose something. You know, when we have a sigma bond, we have something called free rotation. We rotate freely because this overlap's not broken. But when we have a pi bond, there's no free rotation. Like I can't rotate this oxygen or spin it this way or that way. Because in order to rotate it, it would require breaking the pi bond. And so for pi bonds, there's no free rotation, but for sigma bonds, there is free rotation allowed. And so we can have what are called different conformations. We can see that here. So for example, if I look at the other oxygen here, here. And so the way we represent the pi bond here is like this. We show just one carbon, an sp2 orbital on this carbon bonds here, and a p orbital in a bond here. Yeah. And then again here. Something like that. And so this shows one atom bonds in 2 places. The double bond. One atom bonds in 2 places. Double bond. Okay. Don't write it like this. I don't want to see people writing it like this because this makes it seem like they're 2 different oxygens. Yeah. There's just one oxygen bonding in 2 places. Now, what about the other stuff? Well, let's take a look. We're going to call this oxygen 3, this one coming out here. Oxygen 3, what's a hybridization on oxygen 3? This was oxygen 1. Oxygen 3 is going to be, so what is that hybridization? sp3. Oxygen 3 is sp3. So let's take a look at the energy level diagram for oxygen 3. I'm going to erase this here. Oxygen 3, how many sp3 orbitals are there? 4. How many electrons does that oxygen have? 6. And so 1, 2, 3, 4, 5, 6. 2 lone pairs. Are there 2 lone pairs? Yeah, there's 2 lone pairs. We always fill the diagram based on the Lewis structure. These diagrams are always filled based on the Lewis structure, not on what you think it's going to be, but what it shows in the Lewis structure. This is why we always write the Lewis structure first. All right, so it's sp3. Now, how do I draw sp3? I can draw sp3s like this. Okay, now the perspective is going to get complicated because this is coming out, so we're just going to show this kind of in the same plane as that. And then we do 2 in the plane, like this, and then 1 coming out, like this, and then 1 going in. And so what it looks like is, it looks like a little tripod. Whenever you do sp3, no matter what the angle is, let's say this is the point of attachment. This is the point of attachment, the other end is going to look like a tripod. You know, even though it's an even tripod and there's no one line. And so this is kind of like this. But what we do is we rotate it so we get at least 2 legs in the plane and then 2 out, you know, as we draw it. And now this is tricky because this is coming out, but, you know, we're not worried about it. And we just kind of want to show it. And so here, on this, we're going to get sp3. Okay, now I blew it again because can these be spin up? One of these cannot be spin up. So this one will put spin down. So this is going to be spin down here. This is going to be sp3, sp2 sigma bond. sp3, sp2 sigma bond. Right here. Then I got two lone pairs. The two lone pairs, I'm gonna put one lone pair in this orbital sticking out and one lone pair in this orbital that sticks in. I got my two lone pairs there. Maybe that's not so visible, is it? Okay, so that means the carbon, sp2, comes in here and bonds here. And what's this other one? Well, this other one's going to be, it's bonded to the hydrogen. Hydrogen's simple enough. Hydrogen's just what? No hybridization, it's just a s orbital, right? So this is a hydrogen s orbital. And so I'm going to put this one spin up, and therefore hydrogen is going to go spin down. And so the hydrogen s orbital comes in here, and then we're going to bond it spin down. Then we have one more oxygen. We have this oxygen 2. What's the hybridization on oxygen 2? sp3. And so for oxygen 2, you know, how am I going to draw that? This is so complicated here. And so I'm just going to do the same thing. 2 in the plane, right? 1 coming out, and 1 going in. And so oxygen 2 is going to look like this. Oxygen 2 is sp3. And how many electrons does oxygen 2 have? 7. 1, 2, 3, 4, 5, 6, 7. So 3 lone pairs and 1 bond, right? But again, I got to flip this electron, the opposing spin, because what's going to come in here? Well, carbon's going to come in here with an sp2. Carbon comes in here with an sp2. It's going to fill this orbital here. So oxygen. And so this one I'll put spin down, and then I'll put lone pairs in these other. Do you see that? Can you kind of visualize it? If we were to draw this three-dimensionally as a Lewis structure, it would look something like this. It would look like, well, I'll try to draw it as a Lewis structure here. I'm going to have a carbon here, and then this oxygen here, which is going to be a double bond here. And then one lone pair is going to stick out here, one lone pair is going to stick in here. And then I have a bond coming out here, and a bond going in here. The bond coming out is going to an oxygen here, which is going to flip down to a hydrogen here, and then this is going to come out and then go in with a lone pair. Oops. Just try to draw it again. The lone pair sticks out here, and the lone pair sticks in here. Now, this is kind of not perfect, but it's okay. Then we'll have a lone pair in the plane, a lone pair sticking out, and a lone pair sticking in here. So we got 3 lone pairs on this one with a negative charge, and that's what it looks like. You have to note that there's free rotation here. On here, like for example, if I rotate the hydrogen around and around the tripod base like this, there's no problem because it's not going to break the bond. And so the hydrogen position, we can position it anywhere in this space here. I just positioned it here because I just want to draw on the plane of the board. But it's not really in the plane of the board because this sticks out. But and so just as long as it seems somewhat accurate, we're okay. All right, this is what we call the side view. I want to draw the top view of this. The top view will look like this. here. Just gonna have to move the computer back and forth. So she'll just erase it. The top view will look like this, where put it in the plane. So this is true planar and 120-degree angle here. We get an oxygen. Now, what I want to do is I want to keep the hydrogen in the plane. I want to keep as much in the plane as possible. So I'll rotate this until it's in the plane, which means one lone pair will stick out, and another lone pair will stick in. And then over here I have this oxygen. And so I'll put one lone pair in the plane, it doesn't matter which, and then one lone pair sticks out, and then one lone pair sticks in. Or something like that. Kind of tetrahedral. And so I'm going to draw it. Erase this one. Erase this one. And so if I draw this, I'm going to have the carbon with sp2 here in the plane, and then another sp2 at 120 angle in the plane, and another sp2 at 120 angle in the plane. These should be equal in size, but drawing's not so great. And then I got an oxygen with an sp2 here, and then two sp2s in the plane. Okay, now where's the p orbital? Can you tell me where the p orbital is? Yeah, perpendicular plane. So I got a p orbital here and a p orbital here. It's sticking straight out. So one lobe is sticking straight out, another lobe is sticking in. So those would be my lobes. And so I'm not going to draw a line here because that might kind of interfere with the sigma bond, you know, just visualizing the sigma bond. And so what we do is we kind of draw a curved line here. So if we draw a straight line here, it looks like sigma. I might get confused with sigma. But basically it's a head-on, direct, side-to-side, parallel overlap like that. And then we'll fill these with electrons. We had this. And then the P, you know, we had the PP pi bonding electrons. So we put carbon is spin up here. That means oxygen will have to be spin down here. And that's one PP pi bond. And so this is one p orbital here, one p orbital. So we got a PP pi bond, and then a sp2 sigma bond, which completes the double bond. And so this is looking, now compare the top view with the side view. You see all we're looking at is looking at it from the top of the p orbitals versus the side of the p orbitals. That's the difference between the top view and the side view. Now, over here we're bonding this to an sp3 oxygen here. So the sp3 orbital. sp3, we draw two in the plane, and then one coming out, and then one going in. And so carbon has spin up, and therefore, then I got two lone pairs here, and then this oxygen I made spin up, and then the hydrogen, which is an S, I made spin down. And then we have another oxygen over here, which was sp3 here, and then this has two lone pairs, so we'll just draw an sp3 in the plane, one coming out, and one going in. That's 1, 2, 3 lone pairs there. Carbon spin up, oxygen spin down here. And so looking at this, we have the sp3, sp2 sigma, and then over here sp3, sp2 sigma. Then what we can do is we can map out the electron cloud, you know. It's going to be polarized, of course, to the oxygen because oxygen is more electronegative. But we can kind of draw the dots and get an idea of the, I missed the lone pairs here. get an idea of how the electron density is distributed in the molecule itself, right? And what orbitals and that kind of stuff. So this will do the valence bond analysis for bicarbonate ion, showing a double bond. Now, a triple bond is going to have 2 pp pi bonds and 1 sigma bond. Do you want to do a triple bond? Okay. Maybe, maybe not. Maybe we should do that. Let's do acetylene, which is the simplest triple bond here. What is the hybridization on carbon? sp3b2 is not correct. sp2 is not correct.
Just pick one carbon, not both carbons.
sp. Oh, it's sp because you look at carbon, we have a single bond and a triple bond. That's just 2 groups of electrons. The triple bond you can't split apart. It has to be taken as a collective whole. And so it's sp hybridized. And so if we look at carbon, which is sp hybridized, we have how many sp orbitals? 2. How many electrons does carbon have in the structure? 4. So 1, 2, 3, 4. Does that look right? 2 lone pairs on the carbon? Less than an octet? No. Because we're missing missing orbitals, aren't we? It looks like carbon has an octet. Carbon does have an octet, 2, 4, 6, 8. So we need 4 orbitals. So what are the other 2 orbitals? P orbitals. We have unhybridized P orbitals. There are no lone pairs. So this is what I mean. We always fill the diagrams not on what we think, but on what the Lewis structure tells us. It's always the case. So let's go ahead and draw this out. When we draw this out, we got carbon sp here and another sp here. Carbon. There's 1 electron in this sp, 1 electron in this sp. Okay, on the left it's bonded to a hydrogen. And so hydrogen must come in here with an s orbital and bond here. So hydrogen comes in here with an s orbital and bonds. So hydrogen s. I'm not consistent here. You could just, I put the s here just in parentheses because hydrogen's kind of small, so I don't want to put the h in the center. So that's why I did it. I don't know. Some people draw hydrogen like this. I've seen hydrogen drawn like this. Is the nucleus outside the 1s orbital? I've seen that so many times. I don't understand. Anyway, let's continue on. Okay, this is going to be bonded to another carbon, but the carbons are the same. Do you see that? And so this second carbon, which is called carbon 2, is going to be spin down. And so there's my carbon. Carbon's going to come in here with an sp. See that? Spin down. And we form an sp-sp sigma bond. So that's our sigma bond. And then this carbon will do spin down. It's going to be bonded to another hydrogen. And this hydrogen will put a spin up. Like that. Now, how should I draw the p orbitals? Well, I'm going to have 2 unhybridized p orbitals. One on the z. We've got the pz here. The pz is in the plane. And then one on the py. The py is in the plane? No, the py is out of the plane. This py I'm going to draw a little differently. This py, the other py I drew as a circle. This py I'm going to try to tilt it at a slight angle so we see it. This is going to be the py here. Just kind of tilted.
So let's tilt the molecule a little bit so we can see it on the side a little from the PZ here. This is PZ. And so this PY here, I'm tilted at a slight angle here so we can better see it. Now the PZ and the PY are both going to have electrons. So in this carbon here, I have a PZ electron. It doesn't matter which one I pick here. And I have a PY electron. Let's put both of those spin out. Okay, that means on the other carbon they got to be spin down. So on this one, we'll put this one spin down here. And this one spin down. Do you see how they're lined up? What's going to happen? We're going to get a PZ-PZ pi bond. See that? And a PY. This time I'm going to draw lines because I think it's not going to interfere with the sigma bond there, rather than curved, thing that it did earlier. Okay, so do you see the triple bond? Sigma, pi, pi. We've got the green pi, the blue pi, and the black sigma. That's a triple bond. Triple bonds are stronger and shorter. They're going to be shorter because we got 6 electrons in there. So when we're looking at the electron cloud it's got a lot more electron density, which is going to pull, we got the sigma bonding electron density here. We got the PZ bonding electron density here. And we got the PY bonding electron density here. And so all that electron density is going to pull the 2 nuclei closer, and it's going to hold them more tightly together. And so triple bonds are quite a bit stronger than single bonds and double bonds. Okay. Are we good with that so far? All right. We can do more complex molecules too. But let's look at the next one is the conjugated systems. Sometimes resonance forms are not so difficult to see. Let's look at conjugated. Conjugated systems are extra stable. And what we see in conjugated systems is this. Sometimes conjugated are called aromatics. When we have a conjugated system, we have alternating double and single bonds. Alternating double and single. And something special happens with a conjugated system. Let's take a look at the classic conjugated systems, like maybe ozone. Well, yeah, we'll do benzene. Benzene was a hexagonal ring like this with alternating double and single bonds. Like this. And it's a very interesting molecule. It's flat, like a pancake. It's because all the carbons are what? Hybridization. sp2. And the Mg, molecular geometry around each carbon is sp. sp2. sp2s. And so what's going to result here is, this is all trigonal planar. And we can get a resonance form for this. Which looks like this. Organic chemists get tired of writing all the atoms out. And so in organic chemistry, benzene's written like this. The left one would be written like this. This is a representation of the left one. And the right one would be written like this. And so you have to write, so many structures out in organic, and so it gets tiring. So what we do, they have this shorthand method where they just show the bonds. Not all the bonds, they just showed like carbon-carbon, carbon-nitrogen, those bonds, but they don't show the carbon-hydrogen bonds. The carbon-hydrogen bonds you fill out based on how many bonds carbon likes to form. And so the hydrogens are there, they're just not shown because this is just a simple structure. Well, here's where I want a PowerPoint slide because I'd rather not draw this, but now I have to draw it. I mean, of course, you have to know how to draw it. All right. So how should I draw this? What I'm going to do is I'm going to do kind of a side view, just a tilted side view of this. Do that. Tilted side view. Each of these are sp2. Let's see. In order to do the tilted side view, I need to draw a little bit. Kind of see. Yeah. So let's do the sp2 orbitals in blue. sp2, sp2. This is the sp2 sigma bond. And then we have an sp2 here out to a hydrogen. Right? There's going to be a hydrogen S here. And the sp2, 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 etc. So we have a bunch of sp2, sp2 sigma bonds. And of course, there are going to be electrons in here. And then all these are getting bonded to the hydrogens here. I'm not going to do it full 3D because it's tough to draw. But can you kind of see it? Or is it getting too messy? So we have an sp2 sigma bond network. Now let's do the pi bonds. So I'm going to pick this structure here. So the first pi bond is here. This p orbital here. It's my first pi bond. The next pi bond's over here. We got alternating pi bonds. Next pi bond is over here. Do you see that? Now, you take a look. Look at these two p orbitals are adjacent to each other, right? But so are these two. Do you see these two p orbitals here, even though there's no pi bond between them, are adjacent to each other? And so what happens is this. What happens is all these pi bonds are lined up. So they all overlap. See that? So in other words, if I'm looking at the pi bonds, let's look at the top view. I got a pi bond here, I got a pi bond here, I got a pi bond here. Well, what's preventing it from overlapping all the way? Nothing. And so it overlaps. And so in this case, it kind of looks like a hybrid, because what we can do is we can spread out all the pi electrons over all the p orbitals. If we do that, then we get this. This is the classic structure of density. This is the hybrid structure. This is benzene here. Do you see the pi bonding electrons can be spread out over the entire molecule? This is called delocalization. And so here in the green, the red is delocalization of the pi bonding electrons. Delocalization. Pi bonding electron. This leads to extra stability or unusual stability. And so this is what we call localized here. And so we have a pi bond that's localized between two carbon atoms. This is the localized. In fact, all these are localized because we picked two specific atoms. Here, this is delocalized. And so all delocalized means is that you spread it out. It's like water. You know, what happens is we want to put 2 feet of water, 1 foot, 2 feet, 1 foot, 2 feet, 1 foot. But unfortunately, there's no wall. Is there a wall between these p orbitals? There's no wall. And so what's going to happen is it's just going to spread out. The whole cloud is going to spread out. Because there's no wall. That's because all the p orbitals are right next to each other. Now, this is not a conjugated system. So for example, if we had this, if we had a system like this, this is not conjugated because we have this sp, let's call them sp3. We have an sp3 carbon here. And so that's going to break the conjugated. That's, you know, it's not going to happen here. In other words, I'm going to have localized pi bond here and a localized pi bond here, and I can't delocalize it because it's not alternating. Do you see? Because there's going to be sp3 stuck in the middle here. I'm disrupting my. And so benzene does this. In fact, other molecules do this as well. In fact, shoot, I was going to show one. But since the failed, let's see. I was going to do sometimes this extra stability that you get from delocalized electrons is going to change what you might think would be the hybridization of the atom. And so let me just show you an example of that here. Okay, let's take a look. HCO and H2. This is going to be problem number 57.
Let's draw the Lewis structure for this. Okay. And it looks like this here.
And then let's take a look at the angles here. These are the approximate bond angles in this. Okay, we have an HCO angle of 123 degrees. Actually, let me just draw them in the structure.
Does that sound about right? 123 degrees.
An HCN angle of 113 degrees. HCN, 113. An NCO angle of 124. NCO, 124. An CNH angle of 119. CNH, 119. An HNH angle of 119.
And this must be 119 too, even though that doesn't add up to 360.
It doesn't add up to 360. It could be not totally flat. It's tilted, then it doesn't have to add up to 160. I mean, excuse me, 360. Okay, then they give us one more bit of information. That is the CN bond length is 138 picometers.
So the CN bond length is 138 picometers.
CN bond length of 138 picometers, what does that put us? And so if we go back to chapter 10 and look at the bond length table and see a CN bond length is this. A carbon-nitrogen single bond is 147 picometers.
And so from table, chapter 10, carbon-nitrogen single bond, 147 picometers. A carbon-nitrogen double bond
It's going to be shorter, Carbon-nitrogen double bond is a 128 picometers. And the carbon-nitrogen triple bond is 120 picometers. All right, so what do they want in this question? Let's see. I can't project this, unfortunately. Just to see that. But they want two Lewis structures can be written for this molecule, with the true structure being a resonance hybrid of the two. Propose a hybridization and bonding scheme for each structure. Well, this is one Lewis structure. I don't know what the other one is, but let's think about this. Propose a resonance and bonding scheme. Let's just propose a structure for this. Does this, looking at this carbon, what's the hybridization on the carbon here?
SP2.
SP2. Does the angles look right? Well, it's going to be distorted because we've got a double bond. And double bond has more repulsion than a single bond, so it's going to widen these. You know, we would have guessed this is 116 and 122 and 122, right? Roughly. And so it doesn't look bad. This looks okay with the distortions due to the double bond. Is this a localized double bond or a delocalized double bond? This is localized. This is between the carbon and oxygen. It can't. Where else can it spread? What's the hybridization on nitrogen? SP3. Do those angles look right? No. If you see angles like that, it doesn't look SP3. It looks SP2. And so this nitrogen's got to be SP2 hybridized, not SP3 hybridized to generate angles like that. Why so? And so why so is because of this. This is very weird. You know, should be SP3, but angles tell us it is SP2. Because the number of groups tells us. Now, why the heck? Well, there are two, there are two reasons to hybridize. The two reasons are, one, to minimize repulsions, and two, to maximize bonding. And so why hybridize? Minimize repulsions, maximize bonding. Minimize repulsions and or maximize bonding. Now, what's the advantage of, if I do SP2, then I'm going to get, I'm going to get more repulsions, then, aren't I? Because if I have 3 groups of electrons, SP2 is quite good. But if I have 4 groups, the maximum angle I can get is 109, whereas SP2 I'm going to get 90. 90s aren't good, are they? Because if I were to hybridize nitrogen as SP2, you know what I'm going to do? I'm going to do tilted side view because I don't want to spend too much time on drawing this top view. Now, SP3 makes sense to minimize the repulsions. And so if I have 4 groups, I've got, actually, how should I write this? Since I'm writing it like this, I'll write 2 in the plane, 1 coming out, and 1 going in. Double line there. And so I got a lone pair and 3 bonds. And so I want to maximize the distance between all 3 groups. And so, you know, what do I have? I have two hydrogens here. Hydrogen, hydrogen here. H, H. And then over here I got this carbon. This carbon's what, sp2? Carbon's sp2. So I got something like this. So I need to kind of spread those four groups out as far as possible to minimize the repulsion, correct? But if I have the nitrogen as sp2, so let's do that here. And this is going to be tilted side view again. Do that. If I have the nitrogen as sp2, it's going to look like this. So let's draw this sp2 coming out, this sp2 going in. And so that means there's going to be a p orbital here and hybridized. And so it looks like the hydrogens are going to be bonded to the sp2 here. And the hydrogen bonded to sp2 here. The hydrogen carbons here. Now where's that lone pair? The lone pair is here now. Does that look good for repulsions? Because now I have a lone pair and then these three bonding pairs at a 90-degree angle. Is that good? It's not good. The repulsions are greater. And so this is not minimizing repulsions. This must be for maximizing bonding, but how, you know, this just a single bond there. How am I going to be maximizing the bonding in this case? Well, the maximizing the bonding is going to come from this. The maximizing the bonding comes from the fact that carbon is also sp2 hybridized. And so if I think about carbons, it's going to be like this. And sp2 is coming out here, sp2 is going in here. And there's going to be a p orbital here. There's p orbital here. P orbital. But then I also have this oxygen here. What's the hybridization on the oxygen here? sp2 as well. And so I'll draw that oxygen out over here. This oxygen is going to be sp2 as well. Lone pair and lone pair. Then I got these electrons here. And so I have a pp pi bond like this, right? A localized pp pi bond. However, if I rehybridize nitrogen as sp2 instead of sp3, do you see what's going to happen? All three p orbitals line up like this. And I get a delocalized pi bonding network. Can you see that? And so this is the reason why. The reason why wasn't to minimize repulsions, it was to maximize the delocalization of electrons, which is going to help stabilize the molecule. The more we can delocalize electrons, the stronger the bonds and the more stable it becomes. And so benzene has unusually strong bonds because of the delocalization of the electron density. And so the two resonance forms that result are going to look like this. This is advanced. This is advanced carbon. Even though it's number 57, it's in the advanced section. And so the two resonance forms look like this. That's one. And the other resonance form will be like this. If I take this lone pair and drop it into the bond and take this bonding pair and bring it to the oxygen, that'll make an oxygen with three lone pairs and a negative formal charge. And I have a carbon here, and then I got this going down here, like this. And it's going to put a positive formal charge here. And you think, wow, that doesn't look like a great structure, you know? Here, it doesn't look like such a great structure because we've got these formal charges that pop up. But because of the delocalization of the pi bonding network, that's what the payoff is. Because looking at this, I would have said no. No. But because of this, you know, when we have these alternating single and double, although this is not really alternating, this is something that can be done because nitrogen has that lone pair. We have that, then it can happen. Okay. Anyway, an advanced topic. So sometimes what we predict for the hybridization isn't what we see because there are other factors involved here. Let me tell you another one. Let's look at H2S. Another example. What do we predict for the hybridization? Sulfur. sp3. So we predict sp3. What do you think the HSH angle is? Just tell me what the HSH angle is. A lot of people tell me the HSH angle is 180 degrees. Oh, it's 100. Look at that. Looks like 180 degrees. However, if I draw it like this, a lot of people will tell me the HSH angle looks like it's 90 degrees. 90 degrees. So which one is it? Is it 90 degrees or 180 degrees or neither of those? Neither of those, because when you draw a Lewis structure, you don't have to be accurate unless you're trying to be. You know, the angle should be what? 109, based on sp3 hybridization. So drawing, make the reference to that. You know, the way we draw it doesn't matter. So don't be fooled. The angle should be 109 because it's sp3 hybridized. Right? And that 109 angle comes about to maximize bonding or to minimize repulsion? Minimize repulsion. You know what the actual angle is? You'd expect 105, but the actual angle is 90 degrees. Close to 90 degrees. 90 degrees. The reason is this. You know, oxygen's a small atom. Small atom, you put groups of electrons around a small atom, they're gonna repel each other because it's a small volume tight fit. But if you have a big atom with 4 groups of electrons, those groups of electrons are kind of far away because it's a big atom. Right? And so the bigger the atom, the less significant and the less hybridization we get. And so sulfur is a big atom, it turns out. It's a big atom. And so it's not 90 degrees because this is the right way of drawing it. It's 90 degrees because we don't have hybridization. Minimal. In other words, what we see is something like this. Sulfur is going to have an s orbital. This is 3s and 3p. Normally sulfur has how many valence electrons? 6 valence electrons, like this. And what's going to happen is the hydrogens are going to come in with their s. And the situation with sulfur is those p orbitals are so big that we don't have to worry about the repulsion. So this is a PZ, and then this is a PX here. And then the PY is going to have a lone pair in there. So we'll put the Py with a lone pair, the Pz with a single electron, the Px with a single electron, and then we have the S. And the S we'll just put with a lone pair in here. The S. And it turns out that these electrons, as the atom is so big and these orbitals are so big because we're in the n equals 3, that they can still get far enough apart from each other that the repulsions are going to be minimal. And so what we're going to get is this, a Ps sigma bond here, a Ps sigma bond here. And over here, the same thing, a Ps sigma bond. And so the bigger the atom, the less hybridized it is. The smaller the atom, more hybridized it's going to be. And so there are going to be different degrees of hybridization depending on the angle. The angle can tell us, you know, how hybridized it is. You know, is it closer to sp? Is it closer to sp2? Is it sp3? Where is it? And so these orbitals are big. Well, that being the case, we're not going to guesstimate, you know, when does it turn big enough? When does it turn small enough? You know, this is too much hassle, and that's too much detail. And so you should just make a quick note that, you know, the level of hybridization changes. And so, and we saw that, and so we keep this in the back of our mind, but what we're gonna do is we're gonna just hybridize it. And so what we'll do is we'll hybridize all atoms. And so for us, we hybridize everything. Because it's like percent ionic, you know. What are you going to call? Are you going to call a metal and a non-metal an ionic bond or a covalent bond? You'd call it an ionic bond. But you know, how ionic? Is it going to be 80% ionic, 90% ionic, 70% ionic? How ionic? We aren't going to worry about it. We're just going to call it ionic. And the same thing here, you know. For example, if we had an angle of 100 and like 115 degrees, you know, that's getting close to sp2. So this is on its way from sp2 to, but it's also between sp2 and sp3. You know. Well, what percent? Well, we can figure out the percent S character and the percent P character based on that, but we aren't. You know. So what we're going to do is we're going to hybridize everything. And so for us, we would have written this just using sp3 hybrid orbitals. This is easy. And which is right? Well, actually neither is 100% right, you know, so it's okay. Now Petrucci does something very funny. Petrucci hybridizes the central atom, but does not hybridize the terminal atom. And so, for example, Petrucci, what he does is like this. Petrucci. Let's say if I had this. So this carbon would be sp3. What would the fluorine be? sp3. We just say, okay, sp3, it makes sense. Fluorine's a small atom. These lone pairs want to get. But Petrucci doesn't do that. Petrucci will call this bond an sp3p sigma bond because he leaves the fluorine unhybridized. If he leaves the fluorine unhybridized, what that means is it's going to look like this. It's going to look, fluorine's going to look like this, and 2s with a lone pair, and then the 2p. And so here's the p, and so he says a p, sp3 sigma. Well, that's too much hassle. It's too much hassle, so we hybridize everything. And even though H2S is closer to unhybridized, we're going to hybridize it. We're going to call that sp3, and we're going to draw sp3 orbitals for that. Is that clear? And so I'm going to just make it, try to make it simpler. And either way, you know, there are drawbacks, so we might as well hybridize, keep our lives simple. Now, we're going to apply this to acids and bases. So if I'm going to look at this, look at HF.
HCl, HBr, HI.
We aren't gonna worry about size, you know, because the bigger the size, the less hybridization we need to minimize repulsion. We're just gonna call all these halogens what hybridization? SP3, even though iodine's probably not, but it doesn't matter because, you know, it's not gonna change things for us. And so when we analyze this, you know, all the hydrogens are gonna look the same, so, let's do this. My hydrogens, and if I look at fluorine, I'm gonna have an sp3, what? sp3 sigma bond. You know, I got my other sp3 lone pairs here. I'm out of time, but. So what's the difference between HF and HI? Well, HF and HI is a pretty big difference because iodine is gonna have a bigger or smaller sp3 orbital. Bigger, and in fact, it's gonna have a much bigger sp3 orbital. And when we look at the electron cloud distribution, oh, fluorine's more leptonated, of course, so it's going to be distorted. Sorry, I'll do that. Which one do you think is a stronger bond? HF. HF is a much stronger bond. HI is a weak bond. The longer the bond, the weaker it is. This is a long bond, it's going to be very weak. This short bond is going to be very strong. So we'll look at these acids tomorrow. I guess we're out of time now.